everyone, welcome back to Pepcoding. So the question which we will solve today is called Reconstruct Itinerary. First, let us understand the question and then we will head over to the solution. So basically, you have been given a few tickets and these are the stations or the vertices of the graph. Okay. So using all the tickets, you have to visit each of these stations. So if I form a graph of this, it will be something like JFK, ATL, SFO. So from JFK you can go to SFO. Okay. Then from JFK you can go to ATL. From ATL you can go to SFO, or over here it is saying from SFO you can go to ATL. Then from ATL you can go to JFK, and from ATL you can also go to SFO. So your graph will look something like this. Okay. So now what you need to do is that the demand of the question is that you have to use each ticket exactly once. Okay, you have to use each ticket exactly once and visit all the stations. So you have to visit all the stations in a manner such that each ticket is used exactly once, and you have to tell the path which you will use in a way that each ticket can be used once. Okay, so this is your question which you need to do. So basically this question is based on the concept of Eulerian path. Okay, now if you don't know what Eulerian path is, I'll suggest you to go and watch the video. Okay, because without that you won't be able to understand the question and the solution. So please go and watch the video if you haven't, and if you have watched it, we shall continue. So let me give you a gist about Eulerian path. Okay, what happens in Eulerian path is that in Eulerian path you have one vertex which has out degree greater than in degree by exactly 1. Okay, and then there's another vertex which has its in degree greater than the out degree. Okay, so the vertex which has its out degree greater than the in degree by 1 is the source vertex, and the one which has in degree greater than out degree is the destination, and all the other vertices which lie between these two vertex, all the other vertices which lie between these two vertices have their in degree and out degree exactly the same. Okay, so this is what we do when we work with Eulerian path. Okay, so we will work with this concept. When we were working with Eulerian path, we only printed true and false. Over here on the other hand, we have to print the entire path. Okay, so when we are working with the path, normally we would use DFS, that you will add all the path in the way you will travel them. So if I go from JFK to ATL, ATL to SFO, then I will add it in that order only. So JFK, let's suppose I went to SFO, then I went to ATL, and so on. So I will keep on adding them in the DFS, using DFS in the same order. But now we cannot use DFS over here. Over here, we cannot use DFS. The reason is that the question is demanding you to move in a lexicographical order. Okay, we have to move in lexicographical order. So basically what that means is that from JFK we can also go to ATL, we can also go to SFO. When we work with dictionaries, A obviously comes before S, right? So we have to go to ATL first. That is the demand of the question. You cannot randomly go to SFO first. You have to go to ATL first. Now what will happen when we work with it in that manner? See, I say that I start from JFK. We have to start from JFK. It has been given to us that the source is JFK only. So if you remember what we discussed, this means that JFK has out degree greater than in degree. Okay. Now see, over here, if I am working with this graph, I am starting from JFK. I need to move in lexicographical order. So from JFK, I can go to ATL and SFO. But according to lexicographical order, I will go to ATL first. So I move over here. I'll mark it visited. From ATL, I can go to JFK also, I can go to SFO also. So if I work from lexicographical order, I need to go to JFK, but JFK is already visited, so I don't have an option to go over there. So I will go to SFO. Now SFO will be marked visited. From SFO, I can neither go to JFK now nor ATL because both are visited. So what will happen is that we will be stuck in this case. So we need to prevent that. So how will we prevent that? Right now when we were working, we were marking visited for vertices, right? Over here what we were doing, we were marking vertices as visited. But what we should do is that we should mark edges as visited instead of vertices. Because we have the constraint of lexicographical order on the vertices, not on the edges. So we should mark edges as visited. Okay. Now see what we will do when we work with this. I am starting from JFK. Then while working from JFK, I go to ATL first. We are moving in lexicographical order. Then I go to SFO. Okay, since I cannot, in fact, I can go to this. If I work in lexicographical order, from JFK I went to ATL, then I go to JFK. Okay, then this is marked, this is also marked. So you will go to SFO. From SFO, I will go to ATL, and then from ATL, I will go to SFO. Okay, so this is what we do when we are working in lexicographical order, and we will mark edges as visited instead of the vertices. Let me just rub this off so it looks clean. Okay, now we will discuss ahead. Okay, over here. Now see, if we work in the manner in which we were working right now, what will I do if I want to take the paths? I went from JFK to ATL, ATL to JFK, then JFK to SFO, then SFO to ATL, and then ATL to SFO. Now I can see that from SFO I cannot go anywhere else, right? So I will write down SFO and then I will backtrack. Then from here I will again backtrack and I will write ATL over here. Okay, and second, we are moving in the opposite order. So our destination was SFO. We went to ATL after that. After that, I will backtrack again. So if I want to backtrack, I will go back from here. Okay. So over here, I will add JFK. Then again, I'll backtrack. I get ATL. And then again, I'll backtrack. I get JFK. So we wrote down the order in reverse, but we will print from front only. Now, some of you might have it in mind that why should I write it down in the reverse order? Why should I add the paths or the vertices in the reverse order while backtracking instead of adding them from front only? See, we can also do that. If I go from JFK, I went from JFK to ATL. I write JFK, I write ATL. Then from ATL, I go to JFK again. So I write down JFK over here. Then from JFK, I am going to SFO. So SFO. Okay. Over here. Then from SFO, I am going to ATL. Then from ATL, I am going to SFO again. So over here, I think we missed something. Alright, let's see. we were going from SFO, I backtrack to ATL. ATL, okay, right. Over here we need another SFO. We will get SFO, ATL and SFO. So you got these as the same as each other, right? These are the same. So why can't we go in the front order only? Over here we can see that we can go from the front order only. But I am saying that we cannot. See why? Right now we were working with this graph, okay? So working with this graph, it was very easy for us to go in the forward direction also and in the backward direction also. But if I change the graph a little bit and I create another graph, I will not mess with this graph. I will create another graph. Okay. Over here, I'll make another graph. Let's say my graph looks something like this. JFK, then ATL, then SFO, and from JFK I can go to ATL, from JFK and over here. Okay, so this is my graph. Now first we will work for backward direction. That is while backtracking. So I go from JFK to ATL. Okay. And from ATL I cannot go anywhere. So ATL is my destination. I will add it first. And then I will backtrack. Okay. Then from JFK I will go to SFO. So I will go to SFO. Okay. And from SFO I will go to JFK. From SFO I will go to JFK. Then I cannot do anything. I cannot go anywhere. So I will backtrack and I will backtrack. Right. So what we did was we went from JFK to ATL. I could not go anywhere else from ATL. So I wrote it down as my destination and then I backtracked. Then I come to JFK. From JFK I went to SFO and back to JFK. So I will backtrack from JFK. I went to, over here we will make it JFK and then ATL. Okay. So I went to ATL, backtracked. From JFK I went to SFO. From SFO I went back to JFK. So while backtracking I will have JFK, then SFO and then JFK all over again. Okay. But what will happen if I'll move in the forward direction? If I go for the forward direction, let's see what the difference I will have. See, I am saying I'm going in the forward direction, so I will go for JFK, then ATL. Then after ATL, I will not be able to go anywhere. So I will backtrack and go to SFO. Then from SFO, I am going to JFK. So this is what I'll have in forward. But if you look over here and if you move in this direction, it means that you are going from ATL to SFO. Can you do that? No, right? ATL needs to be my destination, but ATL I got in between only. So this will become wrong. So in cases of other graphs, we will get the wrong answer if I go from the front direction, if I add the path from the front direction. So it is absolutely necessary for us to add the path in the reverse direction only. Okay. Now, the next question which comes to mind is that why mark edges, or why do we take visited of edges, and how do we do that? Okay, these are the two questions which we get in mind. The first thing we need to do is we will create a hash map of graph. Okay, so we need to create a hash map. So let's suppose over here I'll make a hash map. Okay, we create a hash map. Now in this hash map I have two things. One is my station where I am at, so that will be of the type string. And I am saying the other one which I want to create is a priority queue. Okay, why am I creating a priority queue? Let's see. I have JFK. From JFK, I can go to ATL also. I can go to SFO also. But I want to, whenever I will retrieve from here, I want to get in lexicographical order. So priority queue will help me do that. That is why I'm taking a priority queue over here instead of any other kind of queue. Okay. Then similarly, I have for SFO. From SFO, I can only go to ATL, I think. Over here we'll see. Yes. So from SFO, I can only go to ATL. And from ATL, I can go to JFK also and SFO also. So this is how my graph will be created. Okay. Then after that, I'll just bring this graph over here so that I can work with it in a better manner. Alright. Now in this graph, what I'll do is, instead of marking the edges, instead of marking them as visited, as soon as I will backtrack and I will be done with the graph, I will simply remove it. Okay. So for example, I went in this path. So I cannot visit this path again. So I will just remove this path. That works as visited only. Now it will ruin my graph, but I think I can work with it. Right? And if there is anyone who wants that we should not ruin the graph, we should keep it as it is, then we can create a hash set and we can name it visited, and in that you can store whether an edge has already been visited or not. That's your choice. That can also be done. Okay. But if you completely remove the edge, that will not be wrong either. Okay. So this is how we are going to work in this question. I hope you understood this part. Now let us try to code it. Okay. So over here, we will try to code this. The first thing which we need to do over here is we need to create a hash map, right? So we will create a hash map of the types string and priority queue of string. Okay. These two we need to take, and I am naming it as graph. The next thing which I am taking is a linked list. Over here, we will write over here. Alright. So the next thing I am taking is a linked list, and the linked list will be of the type string only. Right? Now why am I taking a linked list? Because when I was adding the path for JFK, SFO and ATL, I was moving in the opposite direction, right? I was moving from the back. So I wrote ATL, then let's say it was JFK after that. Then if it was SFO, JFK, something like this. So I'm going from the back, right? So I will use the add first function of linked list. We have the add first function in linked list. So I'm using add first over here. Okay. Then we have a function which we need to create, public static list, and let's name it find itinerary. We are taking a list of string. Okay. And we need to pass list of string to this. Okay. And name is tickets. So this is the function. Okay. Now what you need to do is you will give graph is equal to new hash map, and answer is equal to new linked list. So now what happened is we created them locally now. Since I wrote new over here, we created them locally. So I can work with it over here only. Okay. So now what I'll do, I need to create the hash map now. So for list of string ticket in this which has been given to us, it will be already given to us. So tickets. Okay. In this, I need to work with the hash map. So I need to take the string as my key and the value will be a priority queue. So priority queue of string. What will its name be? Let's say temp. Okay. So in this, I need to get from the hash map itself whether it is present or not. So what I'll do is graph dot get or default. What will this function do? If the key is already present, then I'll retrieve from there. And if it is not present, then I'll create a new priority queue for it. Okay. So for example, when I was working with JFK, I'll check whether JFK is already present. If it is present, then I'll retrieve the value which is present over there. Let's suppose ATL is already present over there. And if it is not present, then I will create a new priority queue for JFK. This is what the function is doing for me. Okay. So for get or default, I will check ticket dot get 0. Okay. Whether its first value is present there or not. Otherwise, new priority queue. What will its type be? String. Right? Okay. So you don't even need to write the type since we are already retrieving it of the type string only. And then I'll close this. Then to this priority queue, I will add the neighbor. So ticket dot get 1. I will add the neighbor. So for JFK, I have ATL and SFO. So I will add its neighbors over there in the priority queue. And I need to put this into the hash map. So graph dot put ticket dot get 0, 10. So this is how we will create our hash map. After that, what I am doing is, after that I will call the function DFL and the source which I will pass for it is JFK. Okay. And we will return answer. Now I need to create the function DFS. So public static void DFS and we have a string source. Okay, now working with this, we will first create a priority queue. So priority queue of string, and we are working with the neighbors in the DFS. We need to add the neighbors to the path. So neighbors is equal to graph dot get src. Okay, the priority queue which is corresponding to a particular string in the hash map are its neighbors only. So I will retrieve that in a priority queue called neighbors. Then while neighbors is not equal to null, there can be a case where there is a vertex which is not connected to any other vertex. So it can be null also. So if it is not null and neighbors dot size. Now another reason why I'll use this is that I was removing the edges. Remember, when I was marking them visited, I was removing the edges. So there may be a point where I'll get it as null. So that's why I need to take care of this condition. And the size of neighbors should be greater than 0. Okay, in this condition what I'll do is, I'll retrieve the neighbor. So string neighbor will be equal to neighbors dot remove. I'll remove 1. Okay, and I'll call DFS for this neighbor now. right? This way we will keep working. This is done. And then answer dot add first. We will add SRC, right? So when you're done with, you come across a vertex from where we can now not go anywhere else, right? That means all the edges have been removed for it. So you will add it to the path and you will use add first, because what we were doing is, since ATL was the destination, we first added ATL. Then after that we added SFO, then JFK. So we are using add first over here. So that is why I use add first. Okay. Now the thing is that I cannot run this view. We are working on the test cases right now. So please have the faith that this is the correct code, and you've already understood the solution, how we will work with it and how we will go about it. So please try it on your own. Okay. So we discussed reconstruct itinerary today, and I hope I was able to deliver it well, and I hope I was able to explain it to you well. So thank you for watching the video. We will see each other the next time. Till then, please like, share and subscribe to the channel. Thank you.